Randall. His title this evening is Terminal Ice Age Floods, Exploring the Landscapes of Catastrophe. Randall, would you like to take the stage?
The Ice Age Floods Institute is an organization that formed back in the 90s when there was first, this whole phenomenon of these great Pacific Northwest floods first started coming onto people's radar screen. And I think when my colleague Brad and I went out there, 97 or 98, they were meeting in in the back room of the Chamber of Commerce in Moses Lake, Washington. And now they've got several dozen chapters spread all over. So the awareness of this phenomenon is growing exponentially, apparently. And this is one of their taglines on their website. It may be the greatest story yet untold. And it is a phenomenal story. We're going to get into just all we're going to be able to do tonight in an hour we have is just get into sort of an introduction. This was the man that did all of the original research going back to the 1920s. Quite a controversial character back in his day. It took literally 2 to 3 decades before mainstream geology was able to accept his idea of these catastrophic floods. And the main objection was that you cannot provide a source for the massive amounts of flood water required for your theory, therefore there were no floods. And at the time, he didn't have really a theory. But he said, well, the evidence speaks for itself, it's there. Whatever the source of these floods were, there's no other explanation. When you put all of the evidence together in totality, there's no other conclusion that one can draw. And it's very much like when you, some of you might be familiar with impact geology now, and you know that to confirm an impact event, a crater, an astrobleem, it's really multiple proxies that are brought in, whether it's shocked quartz or iridium or fallback breccia or vitrified rock, whatever the case may be. It's you bring in all of these things, and in the totality of it, there's really no other conclusion than you're looking at an impact event. It's much like that with the flood phenomenon. We'll go through as much as we can get into in about an hour, and you'll see a kind of a cross section, a sample of what this kind of evidence is involved. In 28, in a famous paper that he did, Harlen Bretz wrote, "The region is unique. Let the observer take the wings of the morning to the uttermost parts of the earth. He will nowhere find its likeness." And in one of the popular books written about the subject matter, Cataclysms on the Columbia, the author Marjorie Burns said the geological detective tale that developed over the Spokane flood controversy is a tale of such sustained intrigue and epic proportions that its unfolding makes most fictional mystery plots seem trite in comparison. And finally, Everett C. Olson, in his introduction to Harlen Bretz's final paper on the subject matter in 1969, he was referring to an outsized agent operating under extraordinary circumstances. So whatever the cause of this flood was, it was something that was extraordinary and outsized. So we'll start with just kind of the broad overview here so you can kind of get a context for this. This shows North America around roughly 14 to 15,000 years before present. And you see the Great Laurentide ice sheet right here. And then you had the Cordilleran ice sheet here. The area we're going to be focused on is this within this box, which is basically the area where the flooding occurred. If you've heard of the channel Scabland, they're an erosional complex on the Columbia Basalt Plateau, which is a group of Miocene basalts that erupted between roughly 6 and 17 million years ago, and Lake Missoula, which is in western Montana. And so what we're going to be mostly looking at is this area along the southern margin of the Cordilleran ice sheet and the basalt plateau, which is right there. And here's kind of the big picture of what we're looking at, and I can't really see it too well, so I'm going to step down here. This is the basalt plateau right here. And the area that we're going to be looking at tonight is mostly within this. And you can actually see some of the erosional forms here. You see there's 2 of these great channeled Scabland tracks here. They come down here and they're all ultimately heading towards the Columbia River, which is this right here, which is headed out to the Pacific Ocean. Lake Missoula was actually back here in these basins here. This is the Bitterroot Valley, which was one of the distal basins for the Lake Missoula, and this is the Flathead basin right here, which was another big reservoir of the lake. If you can see, this is the Clark Fork River coming up this way, and this was the outlet for the draining of these basins. And here's a digital relief where you can kind of really begin to see much more clear what's going on. Here's very obviously the Columbia Basalt Plateau. And there are two lakes that are of importance in understanding or deciphering this phenomenon. One of them is Lake Pend d'Oreille, which is right there at the southern end of the Purcell Trench, which is this feature right here. This is the Flathead Lake, which is at the southern end of the Rocky Mountain Trench, which is this great downfaulted feature right here. And both of these valleys were filled with Cordilleran glacial ice during the late Wisconsin, which was called the Fraser Glaciation out there in the northwest. And you can see on here, right here is the Columbia going down here and then hooking to the north, and out here by Astoria. There's a large fan off the west coast of Oregon right here that was deposited by the sediment-laden floodwaters. And here's a closer up colorized digital relief of the same area. A couple of things I want to call your attention to here. We don't see Lake Pend d'Oreille up here. We'll get back to that in a second. Here's the Columbia Basalt Plateau. You see the Columbia River coming down out of Canada here, hooking to the west in what's called the Great Bend region, hooks around this way, comes around, and right here, this is a feature I'm going to call your attention to. It's called Wallula Gap. This is where all of this floodwater that was issuing from the north and from the northeast coming over the Basalt Plateau all had to discharge through this one gap right here, which then carried it down through the Columbia Gorge here and then up and out into the ocean. You can also see there's multiple anticlinal ridges along in here that were upfolds probably between 6 and 10 million years ago, I think, that played a role in understanding and deciphering this phenomena. Okay, I'm going to call your attention to this feature right here because we're going to come and take a closer look at that. That's called Grand Coulee. And that gives its name to Grand Coulee Dam, which is the most massive poured concrete dam in North America at the present. It's not the tallest, but it is the most massive. And this feature right here is called Moses Coulee, which is another of the great coulees, which are meltwater erosional tracts that are quite mute evidence of the scale and power of these floods. This is the Okanagan River coming down here, out of here, meeting the Columbia right here in this area. This is the Snake River coming in from the east, and it meets the Columbia right here. It's coming up out of the Oregon-Idaho border right here. This is Hell's Canyon right here. So the Snake is coming up this way. The Clearwater River comes in from the east as well. So all of these rivers are confluent. And then they flow through, this was called Wallula Gap, which is a break through this Horse Heaven Hills anticline right here. And here's basically a map of the region we're going to be looking at. Here is Lake Pend d'Oreille, and here's the Clark Fork River Valley. Now, Lake Pend d'Oreille was the site of the ice dam. The Purcell Trench lobe came down out of Canada this way, blocked the westward flow of the Clark Fork River right here, came down here into the Spokane Valley, and it was this blocking of this westward flow that we presume led to the impounding of this roughly about 520 cubic miles of water in the valleys of western Montana. You'll see Grand Coulee over here, and there's an upper Grand Coulee and a lower Grand Coulee. And you'll see Moses Coulee right here. And what else do I need to point out? I just want to kind of give you the geographical overview, so as we zoom in on these features and look at them from the ground, you'll kind of have a context in which you can place this phenomena that we're looking at. Here is, this is typically, if you tour the area out there, this is often a graphic you'll see at some of the roadside overlooks showing the relationship between the lake basins itself and the erosional plexus, which is the channel Scabland. And you'll notice here, this was the Bitterroot Valley basin right here. Here's the Flathead Basin. This is where I pointed out to you Flathead Lake is. So this was the Flathead lobe of the Cordilleran ice sheet. This was the Purcell Trench lobe right here, which served as the ice dam. And this is the entirety of the erosional complex here. Right there you see is where the waters emanating over the basalt plateau all converged at that outlet right there, flowed through down here. There was so much water coming down the Columbia that here at Colima Narrows, even though it's a large valley, it was insufficient to convey the totality of water, so it backed all the way up here to the southern end of the Willamette Valley, up to 400 feet deep. So that was a phenomenal amount of water. Now this wouldn't actually be technically correct according to the orthodox view of this, because what you've got here is it's showing glacial Lake Missoula at full pool, but it's also showing the entire Scabland complex underwater. So according to the conventional view, this wouldn't actually exist, because by the time the entire channel Scabland was submerged underwater, this basin, lake basin, would have been empty. I don't know if we'll have time tonight. I'm going to get into getting into exploring an alternative concept or explanation for the origin of this flood, in which concept this would actually be more accurate, but we'll see how much time we can get to here. And here's a map of the lake itself. You can see it's quite a complex configuration here of valleys and 180-degree turns, hairpin turns. All of this water had to drain out the Clark Fork River, which is right here. And you can see up there in the upper corner is where the ice dam would have been. And here is a NASA color photograph of two of the great Scabland features. This is called the Palouse Scabland, which is one of the greatest of the Scabland tracts right here. It emanates from just south below Spokane, which is here, and it terminates down here at the Snake River. Over here we have what's called the Telford Scabland tract, and then we have several other things. The Crab Creek Coulee was a spillover out of Palouse, because there was so great was the volume coming down here that even these valleys couldn't hold it all, so it spilled over and flowed over and became, now it's a coulee there called Crab Creek. So these are the two major Scabland tracts. You see that the Telford heads right here at this bend in the Columbia, where it comes out of Canada, makes its westward turn, and just below there is the head of the Telford Scabland tract. So what we're going to do is we're going to kind of take an exploration. We're going to do a traverse of the Palouse Scabland tract down to where it meets the Snake. But before we do that, we'll look at this black and white image. This was taken, I think, in the late 70s, about 500 miles up. Here you see the Palouse Scabland tract. Here's the Telford. And here now you can see Grand Coulee, Upper Grand Coulee and Lower Grand Coulee. And down here is Quincy Basin, which is another key site in deciphering this phenomena. Here is Moses Coulee, named after Chief Moses. This arcuate feature right here is the Withrow Moraine, and that marks the southern terminus of the Okanagan lobe of the Cordilleran ice sheet. It's very easy to distinguish because of the fact that south of there you basically have a rolling Palouse landscape that's under intensive agriculture. But when you get up into the moraine itself, it's so bouldery that there's very little agriculture going on there. So you can see that's very definite line of demarcation there. In addition to Telford and Palouse Scabland tracts, Grand Coulee served as one of the major spillways coming down from here, and then it spread out. Once it got out of the confines of this valley here, right here, it spread out. You can actually see a remainder. This is a cutoff meander that forms Moses Lake, which would have been like the final stages, the final draining of the flood would have left this here, and now it is basically a lake, a beautiful lake with a little town next to it. And this area right here, this gray area, is called the Ephrata erratic fan. We're going to be looking at that in a minute. This is Quincy Basin, and the water's poured down here, and right here is the Frenchman Hills anticline, which sort of served as a blockade across the flow of the water and caused the water to actually part. This is kind of known among geologists out there as the parting of the waters, because one great flow came down this way and another flow came down this way and met the Columbia. And here is a graphic from a U.S. Forest Service artist rendering of the whole situation just prior to the to the breakout of the lake, which is this here, Lake Missoula. This is Lake Columbia, as it's now called, which was a body of water there. And you can see right here is the Palouse erosional forms. Over here is the Telford. But there's something, while we're on this slide, there's something I want you to look at here, because this is one of the things that makes me begin questioning some of the prevailing views of this. You'll notice that the Montana-Idaho boundary here is the watershed divide. And I want you to notice the enormous volume of water that's occupying the catchment basin of the Clark Fork River. You'll notice that it's really almost right up to the divide itself. Now, what you need to appreciate is that right here, this is showing that the ice dam water right at the interface, right at the Idaho-Montana border. At this point, based upon studies of trim lines and high water marks in the valley, J.T. Pardee, back in his 1942 paper, concluded that, and you can actually see this for yourself if I've made this traverse quite a few times through this valley, the high water marks right here in this area are 2,100 feet above the valley floor. So that means, that implies a water depth of 2,100 feet, which is interesting because at 2,100 feet, you're looking at in excess of 960 PSI of hydraulic pressure on the heel of that ice dam, which is something that I think has been assumed with, as being a possibility without really enough critical thought. Because the idea of this ice dam actually goes back to the work of T.C. Chamberlain back in the 1890s, and then brought forward in J.T. Pardee's 1910 paper on glacial Lake Missoula. And then J.T. Pardee was with the U.S. Geological Survey, and his career, his first published paper was on Lake Missoula in 1910, and his final published paper in 1942 was also on it. And those were the only two papers he published on there, and they're kind of like bookends to his career. But it was very controversial, and W.C. Alden, who was head of the Geological Survey back then, actually told Pardee to kind of keep his ideas about this glacial lake on the down low, because although Pardee recognized that he had come up with an explanation for Harlen Bretz's flood. So the thing I want you to notice is that the volume, the extent of the amount of water within the catchment basin of the Clark Fork Basin, the question I constantly and repeatedly ask to myself is, what is the source of that water? Can only be two things: glacial meltwater or rainfall. I can't imagine where else water would have come from. Either one of those things I find to be problematic, and we maybe can get into that some if we have time during the question and answer. But let's keep moving on here. There you see the ice dam. You see Lake Missoula depicted at full pool here, which was 4,200 feet above sea level. Like I said, right here, the valley floor is 2,100 feet above sea level. So, you know, there we're looking at a hydraulic head of 2,100 feet. And here's what is being called Glacial Lake Columbia. Interesting thing about Glacial Lake Columbia is that the southern margin, the southern shoreline of Glacial Lake Columbia is right at, like it says here, call it 2,400 feet, right? Well, 2,400 feet is the is actually the literally the boundary of the catchment basin. You rise to 2,500 feet and it's spilling over because the whole basalt plateau tilts to the southwest. So imagine you've got a saucer that's tilted slightly. So the upper rim here is right at just above 2,400 feet. Well, Glacial Lake Columbia is actually full pool, is the entire catchment basin there. Which again, I'm wondering, where is the source of the water? Because now what you've basically got is you've got a huge volume of water lapping at the toe of this ice dam, and then a mere 30 miles away up here, you've got the ice, the interface between the ice dam and Lake Missoula, and you've got a 2,100 foot hydraulic head. In this view, we're going to see part of Grand Coulee sticking out under the Okanagan lobe. We see Moses Coulee coming down here. This is Quincy Basin, which we're going to look at here. All right, and over here you see the two great Scabland tracts. Here comes the Cheney Palouse down this way. It meets the Snake right here, and here comes the Telford Scabland tract. Comes over here, the water coming down the Telford merged with the water coming out of Grand Coulee. And together they flowed down here and they back flooded into this Quincy Basin. And ultimately, like I said, this was the parting of the waters. Some water flowed down this way, some flowed around this way. This is Crab Creek Coulee, and this is the Drumheller channels. Now, this is a map showing Missoula, Montana, and one of the very first things that was a clue that there was some hydrologic event that occurred in this region was both T.C. Chamberlain in the 1890s and in J.T. Pardee's 1910 paper. One of the things that he mentioned was that looking at these two mountains, Mount Jumbo and University Mountain here, there's something very interesting. This is just outside of Missoula, Montana. And what you see on is strand lines or shorelines etched into the mountain slopes, almost up to the very tops of the mountains. Here you can see this was an old photograph taken in the 30s, I believe, where they're really defined nicely because of the snow. But these represent the former lake. Now, here's the question. Did these strand lines represent individual lakes that formed? Because one of the theories now is that this lake formed and drained multiple times. Somewhere, depends on whose research you're looking at, in some cases 40 times, in some cases 80 or 90 times, right? I have never seen anything specific. My thought is that we're actually just looking at the draining of one lake here, because I've looked at quite a few different lake basins that have drained over the years, and you see a succession of descending strand lines that looks very much like this, but on a much smaller scale. Okay, now we're gonna go down the Cheney Palouse, which is the one on the right. The Palouse is basically just several hundred feet of loess topsoil that covers the Miocene basalts of the basalt plateau. Very beautiful, rolling, highly fertile landscape. The problem is there's only 15 or so inches of rainfall per year. So part of the Columbia Basin project is, the reclamation project is, when they built Grand Coulee Dam back in the 30s, they created a reservoir, an artificial reservoir in Upper Grand Coulee. So this is, in effect, what was covering the basalt plateau prior to the floods. And then when the floods came through, they scoured away the Palouse topsoil, exposing the dark basalt underneath. And the thing I want you to notice here is basically these islands that would have been within the flows. You can see the perimeter of the flows here. In the literature, these are usually referred to as streamlined erosional residuals. So say that real fast 3 times. Okay, that's good. Streamlined erosional residuals. So the water coming down here came down this way and did some very interesting incisions along the where the basalt ridge meets the Snake River coming in this way. And here's a kind of a closer up view of the same effect. And here are these streamlined features that you see within. And anybody, the geologists here, what do these elongated features somewhat resemble? What did I hear? Drumlins, yes, drumlins, exactly. And just for comparison, very similar forms are showing up on Mars. Now, I'm not saying that the Missoula flood was on Mars also, okay, just in case you were wondering. That would be quite an event. This is what one of them actually looks like from the ground. Again, it's very drumlin-like. The Stowe side is the left side, the upstream side, and the right side, which is slightly less steeply inclined, is the lee side. But you can basically see here that that hill is about 200 feet high, right? So this is what's left. We're standing, this picture is taken basically standing in the channel itself. And the Scabland, the erosional part, this is classic channel Scabland right here from the air, showing what is called the butte and basin topography. And this is what basically a very swiftly moving flow of water, anywhere from 200 to 500 feet deep, moving over the landscape at, say, around 40 miles an hour, is going to leave in its wake. It's going to look like that. And see, the thing is that prior to the flood, this was covered with that thick mantle of loess topsoil. Here's another view of why it came to be called Scabland. So this is kind of the classic view of Scabland. This is from maybe 400, 500 feet up in the air. And this is from a famous book, Geology Illustrated by John Shelton. Excellent book. I'm sure some of you are probably familiar with this book. He was a geologist and a pilot. And he took this photograph, and you can see here, this shows very distinctly the flood channels and then the truncated hills of loess right here. And these scarp faces are about 200 feet in height. The flow came through here, washed away the intervening loess, and what you see here is the typical process is that it starts out as a sheet flood, removes the topsoil, then it goes to work on the bedrock, and what it'll do is exploit weaknesses within that bedrock, and then it'll begin channeling, and you can see it's beginning to channel, down-cutting a channel right here. If the floodwaters persist long enough, they will eventually become confined to that channel. And that's what happened with Grand Coulee and Moses Coulee. And this is standing at the base of one of those loess islands, just looking out over the barrenness of the basalt, the Scabland tract. And here you see this, the butte and basin topography is quite distinct here. If you see this right here, this is these buttes of columnar basalt. And then here you have the truncated loess hills that again are about 200 feet high. So this picture is taken standing down in one of the Scabland channels. And this is just like at the foot of one of the loess islands. So I'm just showing this here because all geologists know that there's a scale invariant quality to geological features. And one of the ways we find that scale invariance showing up in geology, particularly in reference to the floods we're looking at here tonight, is in the current ripples formation. This was when Hurricane Ivan came through in 2004. I took these pictures. I was actually able to find enough high water marks on buildings and trees to determine that the water depth right here was 23.5 inches. And you can see the chord length and amplitude of the ripples. You know, you're looking at 2 to 3 inches chord length and about half an inch to an inch in amplitude. Now what we're going to do is we're going to go through a sequence where you're going to see first the topographic map. This is 1 to 24,000 scale topographic map. Then we'll see a aerial photograph. And what you'll see here, you'll notice that you've got these streamline forms right here. And you can see that these were stream channels cut. You see here's one coming down this way. And now what I've done is I've superimposed on that. If we scale back and forth here, you'll be able to see right here. But what I want you to notice is that in a bunch of places, what do you see? What do you see over here? What do you see right here? Ripples, yes. And this was one of the things, now this is one of the relic features by which you can demonstrate that, yeah, there were tremendous flood currents going on here. So not only the streamline forms, but now coupled with these current ripples, we'll look at this one. You see that we've got a stream trough up here, a flood trough up here. We've got another one right here. Let's look at the flank of this hill right here. And you'll see, what do you see? More current ripples. There are other ripples. If you look closely, you'll see that there are ripple formations up here. And then this is classic Scabland formation here. And you'll notice a lot of pothole type erosion, and that's clearly evidence of highly turbulent flows where there's vorticular erosion taking place within that turbulent flows. And that's another thing that we look for in trying to determine whether or not these features are products of catastrophic floods is the pothole formations. Let's just scroll back and forth. You'll see this is actually to the same scale map, same road. You see that? But what doesn't show up on the topographic map is this sort of stuff, the ripples. You see, and the ripples can actually be a paleocurrent indicator. The ripples will tell you which direction the water was flowing, because basically the cross section of the ripple, the stow side is going to be steeper, the lee side, the down current side is going to be shallower. You'll also see that in a lot of the ripple fields, there's a fining down current of the material that's composing the ripples. And you'll notice here again, streamline forms. All of these are maps from the Cheney-Palouse Scabland region, and you'll see these elongated. In some of the literature, these things are referred to as flutes, fluting, and they're basically where the water passed around an obstruction within the current. If we zoom in, we're going to focus in on this area right here. Notice the highway coming across where you got this bump right there. That's what we're going to zoom in on. And let's see what we got going on there. You see, this is the stuff that's really was not visible to human eyes until we had this perspective, until we were able to get up above, first through aerial photography, then through satellite photography. A lot of this stuff is now showing up. You can go onto Google Earth now and you can see the imagery of the channel Scablands in 10 seconds, what took J. Harlen Bretz 20 years to draw his first map, basically, because he had to go by car and foot and horseback to traverse this landscape every season, literally for over 20 years before he was able to compile a map that you can now see, you know, in seconds.
What's the scale of the rivers?
This scale? Let's see.
The vertical scale of rivers.
You can actually see here, there's your scale bar at 500 yards. So if you could do some quick calculations in your head.
How high are they?
Oh, how high are the ripples?
Yeah.
Gotcha, okay. The ripples here are probably not that high. These are probably less than 10 feet, probably anywhere from 3 to 10 feet in amplitude here. We're gonna see some much bigger ones, but, and that's one reason why they're not so much seen from the ground, is because they're subtle from the ground. But not all of them, as we will see here when we go on. And again, I'm just gonna go through these fast so you can see that I could have put 50 or more images like this showing how extensive these ripple formations are throughout the Scablands. You see that there are numerous ripple fields. And then, you know, when the flows become more turbulent, you end up with this ribbed effect like this right here, which has been called ribbed moraine. But you can see the very same kind of thing in any turbulent water flows. Now here's the southern end of the Palouse where it meets the Snake River. And a couple of things I'm going to point out to you. Here comes the Palouse River, and the original channel of the Palouse River is this right here, which is now called Coulee, right here. But because you had this ridge right here, the floodwaters overtopped the ridge and made several incisions through the ridge. So this particular incision here captured the Palouse River, so it no longer follows its old channel. It now takes a shortcut directly over here to the Snake River. So this is the Palouse River and Canyon right in here. This over here is another one called Devil's Canyon, but it is it's dry because the river doesn't flow through it anymore. It pretty much makes this right-angled southerly turn right here. And here is a close-up of where the capture took place. You see the Palouse coming down here. Here's the old channel, but it's deflected to the south right here. This feature here is a giant flood bar right here. And when we go to the next image, you'll see there's the flood bar. You'll see that Highway 261 follows the flood bar right down here. You can see that the flood bar is mantled with ripples. And here's, again, from John Shelton's book, this is the cross-section of Coulee, and we can just do a current flow cross-sectional profile in there. So basically, even though this is one of the smallest of the channels, you can still see it's a mile and a half wide and up to 320 feet deep. So that was carrying a pretty substantial volume of water. If we come back here, here's a close-up of Palouse Canyon, and you'll notice how the floodwaters just created this interesting, just straight line incision right across the basalt, and then it seemed to get more erratic down in this area. And you'll also notice that the streamlining that it did here to the Palouse loess. And here is from Richard Foster Flint's 1938 work, looking down into Devil's Canyon, which is this one over here. So that picture is taken right up here looking down the canyon into it, and then the next one is taken from the bottom of it looking in. And so you can really begin to get a sense of the scale of this thing. That would have been flowing brim full for a short period of time, draining that water coming down the Palouse, large basalt eroded outcrops here, and you can really see the scale of the thing right here. These hills are nearly 400 feet high right there.
Why do you think they're so straight? Those
The basalt, the boulders?
No, those erosional channels, I mean, are they?
Well, it has to be, I'm guessing that it was probably exploiting weaknesses in the rock. You know, because when this basalt plateau was uplifted and those anticlinal ridges formed, it was subjected to a lot of stresses coming from different directions. And I'm guessing what it did was there was probably a fracture in the basalt there that the water found very convenient to exploit. That would be my first explanation.
How do you know that the ripples aren't associated with erosion, associated with those same types of fissures in the basalt?
The ripples, you can actually see, I mean, the ripples are composed of gravel. They're composed of sediment, they're gravel, sand, cobbles, and boulders. You can actually see, I mean, I don't think I have them in this show, but you have looked at a lot of cross sections of ripples, and I'd say it's the internal architecture is consistent. And again, you can see that, you know, in some of them you'll have, you can see typical, you know, foreset bedding within the ripples themselves.
And ripples also display, they indicate what the flow regime was, whether it was upper or lower flow regime.
Yes.
And you can analyze the size of the ripples and the styles and back calculate how much flow.
Yes.
So that's how you know that the ripples are the result of the great scale flow.
And that they're not structural. Yeah. Okay, this is fluvial forms. This is just typical thing you'll see along a lot of, you know, where you have fine sediment, kind of this ribbed moraine look. This is kind of another interesting example of the scale and variance. When you look at some of these, you'll see like over here, you've got this almost parabolic profile of some of these things. And then when we go to the Palouse landscape, you'll see very similar, but again, on a much larger scale. Now, it would suggest that what happened was, again, the initial flood stage was a sheet flood over the Palouse. And then it began to channelize, and once it eroded the overlying 100 to 200 foot thick layer of loess, it then the sheet floods became channelized within the Cheney Palouse and within the Telford. But prior to that, there would have been a lower flow regime going over this Palouse landscape. Would suggest molding it into these softened forms. And almost when you're there and look at it, it almost looks like a frozen ocean in effect.
Like interference ripples. Do you know what interference?
No, I don't.
Interference ripples are when, if you go to the beach at low tide,
Oh,
you'll see in the ponds where the wind will blow one direction and create ripples in that direction,
and then
and then blow in a different direction and create different ripples in that direction.
yes, now I know what you're talking, I just never called them that, but yeah. I think you're probably right. And so here's Palouse Falls. This is one of the cataracts that, you know, the modern day Palouse River is minuscule compared to the size of the original cataract. And you can see some very tortured basalt there when the flood flows came through here. And I think, if I recall right, I think Victor Baker estimated the peak discharge through Cheney Palouse at somewhere up close to 150 or 200 million cubic feet per second. He did a lot of the hydrological analysis back in the 70s that basically confirmed Bretz's more qualitative dealing with this evidence. So there's where Palouse Falls is. And then at the mouth, there's looking below the falls, looking down down the canyon, which is over 400 feet high here. And here's where the Palouse meets the Snake River, right here. And at the mouth, there's two great gravel bars splayed out from the mouth, one going up the Snake and the other one going down the Snake. And to give you a sense of the scale here, let's see, this is Lyons Ferry. This is looking, the Palouse River's coming in here from the left, and this is the Snake. And here are the two gravel bars. The floods came down this way, and you can actually see that how it splayed out this way. And there's gravel quarry operations going on this bar, which has obscured there was at one time very distinct, elegant current ripples on this particular bar right here, which are obscured because of the quarrying operations. But to give you a sense again of the scale, you see the Lyons Ferry Bridge coming across right here onto this. Here comes the highway down this way. And that is the bar, this bar right here. We're looking at that from this vantage point over here. And then here's the other one. There's the Lions Ferry Bridge, and there's the other gravel bar. And it's somewhere around 250 feet above the actual river level. So it's a fossil feature that's been sitting there since the floods were over and hasn't really been modified much at all, except like the other bar is now being modified because of the fact that there are gravel quarrying operations going on. So then there's the Telford Scabland tract. We're not going to spend much time on that. I'm going to kind of keep going, but you can see here this incipient channelization that's taking place here. And each of these is like the stream did multiple separations here, but ultimately all converged down here into this Crab Creek Coulee that flowed over here and met up with Grand Coulee. So here's Upper Grand Coulee, here's Lower Grand Coulee, here's Telford. You can see follow the path of the water right down here, and this water all met in this area right here and flowed into this Quincy Basin. The little town of Ephrata gives its name to the fan, which you're going to see here in a second. But we're going to take a little trip down Grand Coulee, and what you'll see here is right up here is Grand Coulee Dam, and then here's the head of Grand Coulee at the Great Notch. It comes down here. This is the Coulee monocline. For those of you that don't know, a monocline is just a single upward fold in the bedrock, and that's what you've got here, as opposed to an anticline or a syncline, which is a downfold. An anticline is an upfold. A monocline is a single fold, and we've got the Coulee monocline, as it's called, right here. One of the things that Bretz realized when he was looking at this was that when the flow came down this way, it spilled over the edge of the monocline right here. And each one of these little squares is a 1 mile square. And the region that he estimated that the water was spilling over the monocline was right at 4 to 5 miles, and the height was 900 feet. So that would have been probably, for a short period of time, the grandest waterfall on Earth. If you figure a waterfall 4 to 5 miles wide and 900 feet high, and the estimated flow through there was about 300 million cubic feet per second, which is, if you took every river on Earth, every river from every continent, added it all together times 10, you would have roughly the flow coming through Grand Coulee.